In the last video, we looked at the first example, estimating the mean age of mature sugar pine trees in the Cucamonga wilderness, and this involved calculating a confidence interval for a population mean. So far, we've looked at the first three steps to this problem: obtain a random sample. The second step, calculate a point estimate. Then we did the third step, verify the requirements for this confidence interval. In this video, we'll move on to the fourth step, which is to calculate the margin of error, and then after that, construct a confidence interval to estimate the population mean. So remember that X bar is a point estimate. It simply summarizes the results of your sample of 20 tree cores. However, your ultimate goal is to estimate mu, the population mean age of mature sugar pine trees in the Cucamonga wilderness. To estimate the population mean, the first thing that you'll want to do is calculate the margin of error. Let's suppose that you wish to have a margin of error and a confidence interval that have 95% confidence. You would use this formula to calculate the margin of error. And in this formula, there's S, which we've already calculated. It came out to 21.21 years for the sample standard deviation. N is the sample size, which is 20. And what about this part of the formula? T sub alpha over 2. T sub alpha over 2 is called a T statistic, and it's part of a distribution called student's T distribution. We've used the normal distribution in Chapter 7 and Chapter 8. Remember, the normal distribution looks like a bell-shaped curve. So here's the blue curve is representing the normal distribution. For now, we won't go into a lot of properties of the T distribution, but it is important to keep in mind that it's very similar to the normal distribution, except it's usually a little flatter. So these two purple curves are two examples of T distributions. They're symmetrical, but they're just a little flatter than the normal distribution. Since, as a biologist, you wanted the margin of error and the confidence interval to have 95% confidence, this means that your confidence interval will be based on the middle 95% of students' T distribution. And the values T sub alpha over 2 represent the cutoff T statistics for the middle 95% of the curve. One way to find the value of T sub alpha over 2 is to use student's T probability distribution table, which is table 7. So the first thing that will help out is to draw a T distribution curve. So I've drawn this out. I've drawn out kind of like a flat curve. The mean of a T distribution is always 0. We're working with a 95% confidence interval, and that means that it's going to be based on the middle 95% of this T distribution curve, or 0.95. One thing to note is that alpha represents the area of both tails. So both tails left over would be the remaining 5%. If the middle part is 95%, the leftover tails are 5%, or 0.05. And that means that each tail by itself is half of 5%, which is 2.5%, or 0.025. And sometimes you'll see that written as alpha over 2, because each tail on its own is half of alpha. So each of these tails is 2.5%, or in other words, an area of 0.025. To use table 7, you'll need two pieces of information. You'll need the degrees of freedom and you'll need the area under the right tail of the curve to the right of t sub alpha over 2. Degrees of freedom are equal to n minus 1. So the degrees of freedom for this example is 20 minus 1 because our sample size was 20, which is 19. The area of the right tail to the right of t sub alpha over 2 is 0.025. If you go up to the drawing, it's just referring to the area of this right tail. So 0.025. Knowing that information, you can now look up the value of t sub alpha over 2 in table 7. Go to 19 degrees of freedom. Here's 19 degrees of freedom. And up here are the areas of the right tail. We want an area of 0.025. So here's 0.025. Go to 19 degrees of freedom, and it looks like that value is 2.093. That's going to be the value of our t sub alpha over 2. So for 95% confidence and 19 degrees of freedom, t sub alpha over 2 is the 2.093. Now that you have that, you can put all of those numbers into the formula, and it will come out to 9.93. So in other words, the margin of error is 9.93 years. Remember that the units we're using here are in years because we're measuring the age of these trees. This means that you have high confidence, 95% confidence, that the true population mean could be as much as 9.93 years higher or lower than your point estimate of 89.85 years. Now that you have the margin of error, you can calculate the 95% confidence interval. One way to do that is to use this formula. This is very similar to the formula for the confidence interval of a proportion. You're still doing point estimate plus and minus the margin of error, and in this case the point estimate is the sample mean. So the sample mean was 89.85, so it's going to be 89.85 plus and minus the margin of error, which was 9.93, and when you do that, the lower bound comes out to 79.92, the upper bound comes out to 99.78. So that's our confidence interval for the population mean age of mature sugar pine trees in the Cucamonga wilderness. The last thing that you would do as a researcher is to interpret the meaning of that confidence interval. And for now, I'm just going to interpret it as one sentence. One way that you could state it is, we are 95% confident that the population mean age of mature sugar pine trees in the Cucamonga wilderness is between 79.92 years and 99.78 years. And as always, you can word your interpretations differently, but however you word it, you want to mention your confidence. You want to mention what you're estimating, which is the mean in this case, and of course you want to mention the actual interval in your interpretation. One last note, these steps 4 and 5, they both involve inferential statistics. Since you used the results of your sample of tree cores, in particular you used this point estimate to draw a conclusion about the entire population of mature sugar pine trees. Okay, in the next video, we'll take a look at another example of doing these confidence intervals.